Today I'm going to teach you about integrals. So first to start off, if you're watching this video, you probably don't know what an integral is. So essentially what an integral is, it's the exact opposite of a derivative in a sense. With a derivative, we measure the slope at a point. We try to see how fast the graph is changing. With an integral, we measure the collective area under the curve at a point. So if you have the derivative of some function, and then you take the integral of that function, you'll be left with the function. So um, you using the rules of integrals, which we'll go over today, you can find the area under any curve from any 2 points. And it doesn't necessarily have to be starting at the origin, or it doesn't have to be in a specific range. It can be at any 2 points. And you can also find it in a general sense. You can find a functional form in it. So in this graphic I have, the area that is being pointed to from a to b, that'll be the integral from a to b of the function f of x. So how would we find this integral? We can talk about it, but how do we find it? So the first thing is called a Riemann sum, which is an approximation. It's never going to be exact unless you do infinite iterations of the sum. Next is the fundamental theorem of calculus, which is exact. So what do each of these mean? Well, first we have the Riemann sum. So in order to properly do a Riemann sum, you have to graph the function, and you also have to find the value of the function at certain points. The more points you use, and the more exact you are with your with the type of Riemann sum you use, the better the approximation will be. And as you'll see, there's different types of Riemann sums. They're all pretty simple. They all build off of each other. So with the function f of x equals x squared plus 1, what we were looking at the start, we know that f of 1 equals 2, f of 2 equals 5, and f of 3 equals 10, and also f of 4 equals 17. So if we want to approximate the area, we can graph it, then we can mark off each point, then we can connect each point as a rectangle, and we can find the area under these rectangles, and it'll give us a pretty good approximation of the area. Now, with certain graphs, it'll give us an under approximation, and with certain graphs, it'll give us an over approximation. So, if we're graphing this, we're going to highlight each point, because we find the values always, um, unless they're given to you in a tabular form, we use them by plugging them into the function. So we're marking off each point. So f of 0 equals 1, f of 1 equals 2, f of 3 equals 5, and now we have f of 3 equals 10, and then we have f of 4 equals 17, even though there wasn't really enough room to mark 17, so just bear with me. So uh, now we can do a left-handed approximation. So if we want to do a left-handed approximation, it's not overly complicated. All we have to do is we start on the left side if it is a left-handed sum. If it was a right-handed sum, we start on the other side. Then we connect each left point to the rightmost point, or the second right point to that point. So one connects to the next point, the second point connects to the third point, and the fourth point connects to the fifth point, and so on and so forth if we had more points. Then what we're going to do is we're going to find the area under each of those rectangles. So if, like, let's say we wanted to find the area under the first rectangle. Well, we know the height of the rectangle is 1, and we know the distance from f of 0 to f of 1 on the x-axis is 1. So the area of that rectangle is 1 times 1. The area of the second rectangle, it has a y value of 2 and an x distance of 1. So 2 times 1 is 2. Then for the next one, it has a y value of 5 and the same x distance of 1. So 5 times 1 is 5. So we're going to add all those up eventually, um, and then we're going to get a certain value. That's going to be our left-handed approximation. Now, we could also do a right-handed sum, which in this case would over approximate the average. In the case we just saw, it obviously under approximated it because all the rectangles were under the graph. That's important. So on top of this, you could also do two other types of approximations, a trapezoidal approximation and a midpoint approximation. A trapezoidal sum would basically take, you would connect lines between each point, and you'd find the area uh, under those figures, which are trapezoids, and that would give you a more exact answer, but it would not be exact still. So now we can find the literal exact area using the fundamental theorem of calculus, unlike the Riemann sums, even though the Riemann sums can get very close, especially if you have more points, even though we were only using 5 points. So the fundamental theorem of calculus says that the integral of f of x dx from a to b is equal to f of b minus f of a, where f of b is the integral at b and f of a is the integral at a. So you obviously don't know how to find the integral yet. There's with the integral, it's not as simple with the derivative of looking at the function and using certain rules to solve it. You have to think about it. However, if in the form that we have our function f of x equals x squared plus 1, we can use something called the power rule. The power rule states that if the function, which we have f of x, is in the functional form of f of x equals x to the n, excluding constants and excluding constants on the end or coefficients, the integral of f of x equals x to the n plus 1 over n plus 1, which is a lot more simple than it sounds. You just plug everything in. So if we wanted to use the fundamental theorem of calculus on our function, we're going to take the integral of x squared and 1 separately. Now, 1 is a constant, so it's really 1 times x to the 0. So we have 1 times x, the integral of 1 would be 1 times x to the 0 plus 1 all over 0 plus 1, which is going to give us x. Then we evaluate it at the 2 points, and we're going to get 25.3, which is a lot more than what we got with the Riemann sum, because our Riemann sum was a heavy under approximation. Okay, so with knowing the fundamental theorem of calculus and Riemann sums, this has been a basic guide to finding the area under a curve using integrals. Thanks for watching. Like the video if you actually liked it, and subscribe if you want more content. Thank you. Have a good day.